Picture the scene. It's the late 16th century, and Galileo Galilei is leaning over the railing of the Leaning Tower of Pisa. He holds a heavy gold coin in one hand and a light falcon feather in the other, and releases them at the same moment. In our mind's eye, we know exactly what happens next. The gold coin drops like a stone, plummeting in a straight line, while the feather catches the breeze, dancing and drifting lazily on its way down to the grass. This mental image aligns with our everyday experience. It also matches the scientific consensus held for 2,000 years since Aristotle, that heavy objects naturally fall faster than light ones. But there are two problems with this picture. First, the way that feather behaves is masking the actual physics of the drop. And second, the evidence that this experiment ever happened is surprisingly thin.
To understand why things fall the way they do, we have to look at the gap between the story we're told and the physical reality of motion. The myth traces back to Vincenzo Viviani. He was Galileo's young secretary, and decades after the scientist's death, the author of his first biography. Viviani wrote that Galileo climbed the famous tower and dropped objects of unequal weight to prove they hit the ground simultaneously. It was framed as a public humiliation of his Aristotelian rivals, performed in front of an astounded crowd of professors and students. Modern historians find no contemporary evidence for this. There are no letters from Galileo, no university records of a demonstration, and not a single diary entry from anyone who supposedly witnessed it. Viviani likely exaggerated the episode. He was writing to solidify his mentor's legacy, painting Galileo as a lone genius bravely battling a stubborn establishment. The irony is that a story designed to champion the rigorous testing of evidence is itself unsupported by the historical record. If we return to our imaginary drop and accept that the feather didn't fall slower simply because it was light, we have to ask what actually caused it to drift. The culprit is aerodynamics. The Earth's atmosphere acts like a fluid. As the feather falls, its large, flat surface area catches that air, creating an upward resistance that physically counteracts the downward pull of gravity. To see the pure math, we remove the atmosphere and drop our objects in a vacuum. The heavy sphere experiences a stronger gravitational force, but its greater mass brings inertia. The extra gravity is perfectly canceled out by the effort to get that bulk moving. In the equations of falling bodies, the object's mass simply drops out of the math. Without air in the way, every object accelerates toward the ground at the exact same rate. Galileo may not have staged a theatrical drop at Pisa, but that doesn't mean no one else in Europe was doing the physical work. In 1586, several years before Galileo's supposed stunt, a Flemish engineer named Simon Steven and a local lawyer named Jan Cornets de Groot conducted a documented drop experiment. They carried two lead balls, one 10 times heavier than the other, up the Nieuwe Kerk church in the Dutch city of Delft, and dropped them onto a wooden platform 30 feet below. They hit with a single thump. Galileo arrived at the same conclusion, not through a public spectacle, but through quiet logic. He designed a thought experiment where he imagined tying a heavy stone and a light stone together, realizing the resulting logic broke Aristotle's theory. The foundations of modern physics weren't built on dramatic stunts. They were built through careful math, through unglamorous observation, and rigorous logic. Yet an itch remained for physicists. As long as humans lived at the bottom of an ocean of air, any visual demonstration of this law would be compromised by atmospheric drag. To show the world that Galileo's math was correct outside of a laboratory, humanity required an environment devoid of air. It took nearly 400 years to reach that stage. In 1971, the Apollo 15 mission provided an opportunity unlike any on Earth. Commander David Scott stepped out onto the desolate surface of the moon, preparing to settle the ancient debate on live television. While scientists had used vacuum tubes for centuries, the moon offered a way to show the world the law of gravity without the constraints of a laboratory. Standing in front of the camera, Scott held out two items: a 1.32 kilogram aluminum geological hammer and a 0.03 kilogram falcon feather. He extended his astronaut gloves, held the objects at shoulder height, and let go. Without a single molecule of air resistance to catch the feather, the two different masses fell parallel to each other.
They drifted down through the lunar gravity and struck the dust at the exact same millisecond. The story of the Leaning Tower of Pisa was likely a fabrication, but the underlying math is absolute. It's the same math that governs the drop of a coin, the fall of a feather, and the motion of the stars.